I ran up right before class again, and it looks like they just made it. So I'll take my answer sheet. And unfortunately, they're not in alphabetic order, and I didn't have time to do so. So I'm sure you're going to make a big old mess up here. But everybody come get yours. You want it. Believe it or not, this is faster than me calling out your name coming down one by one. I've done it. It's all right. We got time. Oh, you know it. At least they show the name so other people can come by and check faster. You know it. That's Murphy's Law. Well, you can finish. You were the yo play, right?
Yes.
I haven't figured out an answer to that yet.
And I haven't done the full experiment, so what I was thinking is taking one, buy them both at the same batch, the same exact batch, then having one just sit on the counter for 24 hours and one in the fridge for 12 hours.
The only thing I have to go is there might be a chemical reaction that changes the pressure in the temperature internally.
And my only other thing was that would it be that it's going, because it's going from such a small contained cold, that it's going out to a warmer?
Well, generally, if things would warm up, they would increase the pressure.
Well,
so it's just squirt out more. Everything else, most things.
Well, if they both reach room temperature, though, wouldn't they? Because the pressure inside is the same temperature outside. The atmospheric pressure would be the same. So when you open it, it would be less. Whereas it's cold, there's more room to expand, going from cold to warm.
There's truth there too.
That's.
Yeah.
I've been thinking about.
But I haven't been able to prove anything. You might be curious. I wrote Yoplait. Read these. Oh. We'll talk after class. Is Anna here? Anna? Shane? Shane, are you here? Okay, that doesn't bode well for either of them. Okay. Okay. The average on the exam was actually a little higher. Oh, yes. Your scores are now online, yes. Yes. This is Brian Jones, not Jerry Garcia. He knows he looks a lot like him. He's the one that got me to have a whole lot of tie-dye in my wardrobe. We made this for him. He's a physics professor at Colorado State University, which is where I was at before here. And he runs an outreach program called the Little Shop of Physics. And our work shirts, every year we'd make a new tie-dyed shirt, put the tour on the back and everything. And whenever we'd get done making the 200-some tour shirts, that's how many volunteers would probably help us throughout the year. There's maybe a core of a dozen or less of us. We'd go out to schools each week, set up things like this in the schools and let the kids come through and help them at least once a week. So he's one of my mentors, and last summer, 2 summers ago, I don't remember now, he won the Robert Millikan Award, which he's a famous scientist, and it was at the national meeting for American Association of Physics Teachers. Pretty much, it just means it's a very big, high honor for people that have done a lot of work in teaching physics, and I learned a lot from him. And this was a shirt we gave him in front of like 500 people to embarrass him, you know. So, Brian Jones, good guy. The test, the average was actually slightly higher than the other two. It was about as low as C as you can get, but hey, we're in the average range. A flip side was there were more Fs than any other test. So it was more kind of spread, which tells me some people got it, some people didn't, or some people studied more than others. Anyway, I'm going to try something new. Shout at me, hate mail right now if you think it's a terrible idea, but I'm going to try it, see how it works. You now have what you answered. You may. I'm going to post. I don't have it yet. I'm going to convert a PDF file of the test and post it in the resources on WebAssign so that you can see the questions again, because I know not all of you took the test. But you won't know the answers yet. And now how was I going to do this? Hold on. I thought I had this worked out in my head. Let's work it out together. My intent was you can correct the ones you missed. Yeah, how do I do this? It would be cool if you could correct the ones you missed, but how do you do that without knowing the answers? Because as soon as you know the answer, then you know the answer. Help me out. I would like you guys to be able to get some partial credit back for this before I give you the answers, the explanations. Suggestions? Yeah, since these came back, I thought, hey, let's do it. Let's announce it today. And I hadn't worked all this through in my mind because I didn't think they'd be this fast. Just repeat that. There we go. So I got to get to you which ones you missed, but not tell you the correct answers to those. Okay, what's that? Yeah, I have it, but of course it's all together, so I can't just like send it you. So I'm sure he doesn't want you to see what you did, but so I can do some work this weekend and break it up. So I got a lot of work, and I'll try it out, see how annoying it is. I'll commit, and email you, or probably easier. I don't know. I'll figure it out. Once you guys know which ones you missed, then I will let you choose again what you think the correct one is. And give you, say you missed 5. Then if you answer them correctly, I can give you half the points you missed. So you can make up half the points you missed on this test. You like that? All right. I was thinking less than a week once I get you of course, what you know you. But you can start thinking about it this week. And most of you probably already have a clue. But yeah, it's fair. I need to get you what you missed. So I'm pretty darn sure that file was there. Which ones? I hope it just says which ones you missed instead of me going through every single question. But I'll work that part out, let you know. If you don't see some email this weekend, clearly I'll tell you about it Monday. And then we'll start the time from there. So thus, I'm not posting the answers or my explanations yet. You have to wait a little longer. Okay. Today, we get to start our last unit. Woo! I'm sure you guys are all happy about that. Well, yes and no, huh? And it's electricity. And I chose this one because it's so ubiquitous. That's a great word. It's everywhere. Most of the things we do, we could live without electricity. Well, we could, but we would. A lot of people would think they couldn't, or they wouldn't want to live without their batteries and powers and cell phones and lights. And if we didn't have electricity, this world would be a lot different place. And so, hey, let's help you guys understand it a little better and appreciate it. And if nothing else, not be as scared by it. A lot of people are scared by electricity, or afraid to touch anything. And some things, rightly so. So by the time we're done with this, at least you'll understand it better. To begin with, chapter 22. Oh, in case you didn't realize, so 22, 23, 24, and 25. 4 more chapters. We'll have the last exam, and we'll be done. Then we'll review lots of stuff. And you get to have the final, of course. But no new material I'll test you on after that. So, electrostatics. We start with charges. That's what causes electricity. And there's 2 types of charges. And I bet you already know what they are. Yeah, AC and DC. Do you know what that stands for? Alternating current and direct current. We're going to get to that, and that's when the charges start moving. So that describes how the charges flow, current. We're not there yet. What are the actual charges that are flowing? What creates that charge? Positive and negative. Very good. The 2 types, positive and negative. Where do they come from? Electrons, and which one are they? Go for it, guess. You're right. Electrons are negative. What's the other one? Protons. They're positive. Do you remember the 3rd particle inside an atom? Right. So we have neutrons, protons, and electrons. The protons and the neutrons are in the nucleus, in the center. Neutrons have no charge. Neutral, neutrons. Neutral, neutron. Yeah, if you get N. Help you remember. Protons, conveniently, are positive. They're in the nucleus. And the electrons are negative. They orbit around. Those are the 2 charges. Electrostatics is just the study of charges not moving. They're static. When they start moving and making currents and flow with electrodynamics. So this is in a sense similar to fluids, where first we looked at air and gases, static, but then when they moved, they could cause changes in pressure too. Bernoulli's principle. So you can think of charges that way as well, if that helps you. Because there's a lot of good analogies between electricity and a fluid. Okay. So I'm going to take this, this is rubber, and this is hair. It's rabbit fur. I didn't kill the rabbit. I charge that one up. It becomes negative. If I charge another one up, just like it, it will become negative as well. So they're the same charge. And do you think same charges, like charges, repel each other or attract each other? You're right. There's an actual force between the charges. And so same charges, like charges, repel. If I rub silk on glass, that'll charge the glass up positive. It will become positive. It's a little harder, so I rub a little more. Make sure it's working. Let's do another positive. And so if I bring this positive near the positive, you expect it to repel. I do too. Let's see if it's working today, right? If we met all of nature's requirements, yes. So positives repel positives, negatives repel negatives. Positives attract negatives. So opposites attract and like charges repel. Whee. There you go. What'd you say? Say that again? How come it changes colors? What changes colors? Oh, these are different materials. This is glass and this is rubber. They're two different materials. They're not changing colors. I'm not trying to... Okay, close your eyes. Open them. Okay, no. They're two different materials. These ping pong balls, if I rub both of them, do you think they'll get charged up oppositely or the same? You're right. Not that I expect you to know, but in case you're curious, they'll get charged up negatively. And you can see that they repel each other. The net negative charges on there repel. And you can actually figure, based on this length and its mass, gravity pulling it down, there's a force down, but now there's an electrostatic force out. And you can resolve those components, those forces, and figure out how strong this force is. And then based on the size of the ball, you could compute how much charge is actually on each ping pong ball. We're not going to do it, don't worry. The bigger they spread apart, the greater the charge. A fun one to try, though, you can do at home. To teach yourself that charge is conserved. Energy is conserved, so is charge. Conservation of charge. If you pull a tape off of a roll of Scotch tape, it just got charged. Charge happens when you separate things. When I rub the rubber and the fur together, it's not so much the friction. They need to make contact, but when they separate, different materials have different affinities, affections, force, if you will, for electrons. You remember in the periodic table, maybe, on the right side, those closer to the noble gases and the halogens, their outer shell of electrons is almost full. So if they had a few more, they'd be happier. So they have a greater affinity for electrons. And materials made out of that type of stuff will grab more electrons. And the other side of the periodic table, they only have a few. So if they gave up a couple, they could go back to their next electron shell and be full and happy. They like that. Anybody remember that from chemistry? So the point is, different materials want to attract electrons more or less than the other ones. That's why, yeah, we've learned that if you rub rabbit fur with rubber, the rubber likes to grab the electrons and the hair likes to give them up. And so this just became net positive. It gave up a few electrons of itself. Where'd they go? Over there, because it liked to grab them. So it has a few more electrons than before. So we say it's charged negatively. It has a net negative charge. This now has a net positive charge.
Does that mean that eventually the rabbit fur won't work anymore to do that?
Theoretically, yes. Yeah, eventually it wouldn't work, because in theory you would get rid of all of them. But if you got rid of all of them, it'd kind of disappear too. But yeah, other things come into play. But there is a limit, and that brings up the point. I keep holding this. I guess I ripped it off sooner than I needed. Here, hold that for me. So before I charged it, like, this thing, is this charged? Let me ask it a different way. Does it contain charges?
Yes.
Positive or negative? Both. Very good. And they're most likely balanced. We'd say they're neutral. It's chock full of charges, protons and electrons. They make up the atoms. They're there, but they're in balance. Any atom that has the same number of protons and electrons is neutral. It has no charge. They effectively cancel each other out, and we can't tell. So these started neutral. They had protons and electrons, positive and negative. But when just grab this one. When they make contact, this grabs some electrons from there. Charge is conserved. It moved around a little, and now this has a few more electrons than this. So this is net positive, this is net negative. We call those ions. Something that gives up an electron, it's an atom that starts neutral. An atom, don't you love it? That starts out neutral. If I give up electrons, that leaves me net positive. I'm a positive ion. But this atom over here grabs the electron. I have more electrons than I have protons now. I'm a negative ion. So the tape started out uncharged. I pull it off the roll, and as it separates, lo and behold, it actually grabs, or one of the two takes electrons. So this actually got charged. And how can I know that? If I do a second one, if they're charged, yeah, they repel each other. And they came off the roll the same way, so they're the same charge, they're repelling. It's not some over-distance stickiness power. This is the electrostatic force between the charges. There is stickiness. This is fun with your cat, but not with me. Okay. So you can show this Coulomb force. It's the guy's last name. The force between charges is Coulomb's law. Coulomb's law. I'm going to write that down in a moment. But here, same charges. They got charged because they separated, and one took electrons than the other. This is fun, though. If you put one down on the table, I've learned to fold over the edges so I can get it back off the table. Piggyback them, stick them together. They should be mostly neutral now because, I'm touching it. I'm allowing charge to transfer between us, and in theory, they're mostly neutral now. I'm going to separate these two. One of them liked electrons more than the other. Now they attract. They're oppositely charged. But charge is still conserved. They just kind of shift it around. When you rip them off that way, one likes electrons more than the other. I don't know which is which. But look, they're both charged. They both attract to me. We're getting to that, though. Okay. Now that I've got tape all over me. So, remember this too, because when we get to the flow of charge, electrodynamics, where do the charges come from? You don't have to go to the utility company and say, yeah, I'd like a bucket of charges, please, so that I can run my toaster. They're already in the materials. Things are made up of atoms that have protons and electrons. The charges are already there. They're already in the wire. They're already in your toaster. They're everywhere. We're just going to make them start moving. But that's not yet. We've got to learn a few more things about charges. Coulomb's law, that force between the ping pong balls. This class likes forces. This is Coulomb's law. What did I choose? Yeah. Little e, help remind me it's an electrostatic force. Some constant. They call it K. We don't need to know what it is. Charge number 1. Charge number 2, and the distance between them. So if you have, charge 1, charge 2, and they're that far apart, then they're going to feel a force on each other. Q2 is going to feel a force on it. Why? Because this charge is near it. And Q1 is going to feel its force. Why? Because Q2 is near it. And let's see. How do you think the force on Q1 compares to the force on Q2? Got 1 vote, 2 votes for equal. Yes, indeedy. Newton's third law still applies. Yeah, the force that this one's going to feel is the exact same force that's going to feel. Even if this was 100 Q. If there were 100 charges over here and 1 over here. Because the force that number 1 feels on 2 is the same as 2 on 1. It's Newton's third law. They have to be the same. It's that tug of war. And the key with Two things where this law comes from. The force is proportional to the charge. If you have more charge, the force is going to be larger. You know, you bring more charge near something, sure, it's going to attract or repel more. That's why they're in the numerator. Those get bigger, so does the force. If you double the charge on both sides, what happens to the force? Double both charges. Make them both 2Q. It quadruples the force. Do you see that? Because if this became 2Q and this 2Q, if you will, you got a 2 here and a 2 there, it'd be 4 times as much. What if you brought them half the distance apart? What would happen to the force? And this is the other key. It's not only what charge you have, but the distance apart. Very important, yeah. If you cut it in half by a factor of 2, then the force increases by a factor of 2 squared, 4. So by cutting the distance in half, you quadruple the force. What if you were to move the charges 3 times farther apart? The force would be 9 times as weak. It'd be a 1/9 as strong. You follow? This is called an inverse square law, and we didn't cover it much, actually at all, because I didn't go there. Gravity. You get outside of Earth, where we're just dominated by the mass of the Earth, but the gravity works because the Earth has mass, and everything we deal with has mass, and 2 masses attract each other. See the similarity? G is some constant, K is some constant. If you increase the masses, they get attracted to each other more. That's why we come falling down to the earth. But it's also an inverse square law. And I hope you know, the closer you get to the surface, the more it attracts to you. If you get out in a spaceship, you're not attracted to the earth as strongly. Anyway, there's a similarity. I wanted to share that with you. What I want you to remember, the amount of charge matters. The distance matters, but it's the distance squared. Very important. That's Coulomb's law. That's the force. I put a certain amount of net charge on this ball and that ball. And so this one exerts a force on that one, and that one exerts a force on that one. In this case, they're the same charge, like that. The force would be outward. Yeah?
So since K is some constant, do we have to know what that constant is?
And if I don't anticipate doing that, I don't even remember if the book tells you what it is, but it's... Yeah, it tells you what it is. If you want to compare K and G, it's in the chapter. What that comes down to is this, the gravitational force, is relatively wimpy, extremely weak compared to the electrostatic force. This is a very strong force between charges compared to the gravitational force. And that constant has a lot to do with that. Yeah? Rubbing them?
Does that stay stable then?
Have you noticed it's gotten a little less, but there's still some charge on there?
So what is it, drawing things from the air? What makes it stabilize? My intuition is that it does stabilize again, but maybe that's not right.
So if charge is conserved, we know that now, and those are starting to relax a little, we saw that, charge must be going somewhere off the ball.
So would you, since you said charge is similar to a fluid, would you say that charge has inertia?
Yes, they have mass as well, so they definitely have inertia, but it's because of their mass. And you're right to your instincts. Where is it going? Well, only if it can have a path to leave. That leads into conductors and insulators. The moisture in the air, the humidity, Water's conductive. It allows charge to flow through it, and it leaks off into the air. So when the air runs into it, some of that charge can transfer to the water molecules. And so leaving less behind, and this becomes less charged, more and more back to neutral. And so there's less charge on them. They feel less force, and gravity brings them back together because that's still acting.
So if they were in like a vacuum or something, would it be the charge will leave?
No, if they were in a vacuum, ideally, yeah, that should stay because there's nowhere for the charge to go. As long as like, the string is a perfect insulator, because that's contacting it too. So slowly some charge can go along the string, but a string is more like an insulator. And so it's helping insulate it from anything else pretty well. Only if they had a way to get to the glass around it. So if there's nothing between the ball and the glass, it can't get there. Good question. Charges are particles. Yeah, they don't get confused with this one with radiation. Radiation needs no medium. And that's a wave. These are particles. They won't just jump. Oh, however, that'd be a fun one. Oh, we're going to do it. I'll remind you back. Yeah, thanks, Bernadette.
You said that it needs a path to escape, like it just can't go into the air. But I guess like to me, like air is a fluid and air is made of molecules. There's like nitrogen and oxygen. Like why not air?
Basically, charge gets conserved, but it needs a path to flow. Charges just don't jump around. They need somewhere to transmit through. And how's it going to get from there to the glass if there's nothing for it to travel along? Kind of like a sound wave. Yeah, they brought up if it was in a vacuum. If there's air, yes. Oh heck, I'm going to do it. Well, no, because I haven't. Well, won't make sense. We'll get to it. So closure, the force on these would be apart. You see that? Because they repel. And if it was positive and negative, they would feel the force towards each other. But you figure it out the same way. And the unit of charge is a Coulomb, named after this guy. The C, Coulomb. And that's a pretty big unit. So if you had 1 Coulomb of charge, that's a whole lot of charge. Yeah. The G is the gravitational constant. This is to remind me and you guys that this force is the force due to gravitational. There's a gravitational field between masses. And this is for electrostatic. Well, this is a force for electrostatics. There's a field between charges. I thought I heard something else. So let's do our insulators and conductors. You can see that at work. This is called an electroscope. And I'm going to charge this up by separating charges. I'm going to transfer them to this. I touch it. So I charged it by direct contact, conduction. The metal in here is a conductor, and when the charge got on there, it could spread out to the needle and everything. They're the same charges. Same charges repel, so there's a Coulombic force between these, an electrostatic force, and the needle repels. We use it as a nice tool because you can see that, look, it's charged. It's insulated from the base, that's why I can touch it. All right, so if I bring a piece of metal, I'm touching ground. I can conduct electricity. Can metal? Yes. So that was charged. Let's figure it out. This was negative. So I'm putting negative charges on here. So that's net negative. So when I touch this, where do the excess negatives on there go? Yeah, they travel through here and through me into the ground, even back out. Now watch this. Let's charge it positive. Same effect because same charges on there. It repels, but they're positive. Let me convince you. This is going to be negative. That's positive. If I bring it near it, what do you expect the needle to do? Do you see it get closer? It's attracting. Whereas if I bring the positive near the positive, it should push it away. Okay. So that is deficit of electrons. It has less electrons because it's net positive. So when I touch this, electrons flow from the ground through me onto it to neutralize it. They can flow either direction. But it becomes neutral because this is a conductor. Allows charge to flow through it. Yeah? When you're charging your car battery, yeah, you got to complete a circuit. And you got to use conductive material, wires, metal, and you got to give it a path for it to move. Yes. Yeah, if you didn't, it wouldn't flow. Like, let's try some more. Let's charge it back up. Plastic. Do you think it's a conductor or an insulator? You're right. Now, whatever little charge was right there on the plate, that transferred to right there. But it can't flow through this to me and away. That's an insulator. So a little bit of charge came off right there, but it can't move through the insulator. What do you think wood is? Somewhere in the middle, huh? But it seems to be conducting a little bit. I would never trust your life to wood. And the wetter it is, the more conductive it is. If they have oils and grime, grease on the outside, it conducts better. Really dry wood is a good insulator. But wood can vary, and there's different types and its conditions. So it can have a little more resistance to the flow of charge. So it's somewhere in between. But that's conductors and insulators. We just charged that by conduction, direct contact. Did you notice too? Yeah, let me emphasize. Oh, for crying out loud. Do you notice that if I charge this up, and I love this. See, you guys are going to be smarter than physics PhDs. I give this demo to, this is being recorded. Maybe I shouldn't say this. Okay, but multiple times I've done this. They come in and they say, that worked better than it normally does. So there's charge on here, and they come up and they just kind of go touch it, and they go, it didn't work. Can you tell me why it doesn't work? Why is charge not transferring to there? Close. It has to do with surface area. The electrons on the outside, in this case, they could be, there's probably mostly on the outside, but they could be inside too. But what's the second thing you said? Yeah, rubber's not, go ahead, Bernadette. Like this way? So touch it this way? Like that? Like that? Come do it, Bernadette. That way I know what you're talking about. Oh, now look what happened. A little bit. We're getting to it. Thanks, Bernadette. She touched it like that and something happened. I'll get to it. You think this is a conductor or an insulator? An insulator. So do charges flow freely on an insulator? No. So wherever they're at, it's like they're trapped in that location. So if I touch it like this, only the charges that are right on the tip can transfer to it. If I touch it here, those charges can transfer. So generally, let's discharge it. I like to go like this. It's like I'm scraping them off, if you will. I'm allowing it to touch in a lot of places so that the charge in each spot can come off. Because it's an insulator. So yeah, now you know why I giggle sometimes at professors, because they come in, it didn't work. Well, you should know that that's an insulator. But they forget, you know. Guess I touched it too much. Okay. So that's charging by conduction. Now let's charge by induction. Charging by conduction, direct contact, induction. The rod is negative. It likes electrons. I bring it near the electroscope and watch what happens. I haven't touched it. So no charges have transferred from the rod to the electroscope. It settles back. What's happening to the charges in the electroscope? If this is negative and I bring it near, what happens to the negative charges in the electroscope? Yeah, they're repelled. So it's like they point away from the rod. And what's that leave the positive charges? Pointing towards the rod. They're attracted. We say that is polarizing the electroscope. Polarizing. It's made up of charges. They're neutral right now. They're balanced. There's equal number of positive and negative. They're in there. So if I bring something negative near it, the negatives point away, kind of rotate, and leaving the positive side attracted. And that's polarized, and you can see an effect. So if I now give some charges a path through me, a conductive path, I'm going to polarize it and touch the electroscope. Are you watching? Oh, look, I took the charges off the electroscope. Now I'm going to let go of the electroscope and remove the rod. I never touched the electroscope with the rod. This still has the same amount of charge. So I charged that through induction, not conduction. I didn't touch it with this. I charged this up, brought it near to polarize it. Look at it this way. If that's negative and the negatives got pointed down and the positives are attracted, when I touch it, I allowed those negatives pointing down to flow through me. So then when I removed things, that was left net positive because it now had a deficit of electrons, less electrons. So this was negative. That's now positive. I took charges away from it. I didn't transfer them directly from here to there. I used what charges it had and removed some of them. Polarize it first so that I could. You guys following me? Wherever I'm touching, that charge comes off, yes. But this charge, at this point I've touched it. Yeah, no charge is flowing anymore, so no. So charging, oh, go ahead, Ines.
Static electricity works the same way when you ground something, it takes the charge off.
Yeah, when you ground something, that's allowing the charge to flow one way or the other to neutralize. Remove charge or bring it back, depending on whether it's an excess of electrons or a deficit. Depends on which way it flows. But yeah, that's how you can think of it. It's neutralizing itself. Now, let's convince you. See, I'm grounding. So any deficit or excess charge left or removed to neutralize it. It's back in balance. Let's charge it negative. Negative. Charge it by conduction. That's negative because the charges went directly there. And we showed you that. Bring negative near it and it repels. Let's charge it through induction. Bring it near. I polarize it. The charges already in the electroscope are rearranged. I'm going to remove them by grounding the electroscope. Ready? Let go. Remove this. Now that has a deficit of electrons. It should be positive. Let's show you. I'll bring this near. Negative near positive should attract. Yep. Are you convinced, or should I get the positive rod out too? So what do you think happens? If I touch it directly with positive, it gets charged. Positive, conduction. What if I charge this by induction with a positive rod? What does that end up? Negative. It's the same game, just the charges are flipping because they're attracted and repelled oppositely. Do you follow that? That's what happens with your balloon. You know, how many of you rubbed a balloon on your head? And then did you try to stick it to the wall? Well, you got to try. Well, I don't try normal balloons anymore. This is the way to go. So, look, charges separate. The latex rubber likes to become negative. It just grabs some electrons from here. We conserve charge, net positive, net negative. This is charged now. Is the door charged? I don't know why it would be. So it's probably neutral. It has charges in it, but they're probably in balance. So these negative charges are going to do what to those negative charges? It's going to repel the negative charges in the wood. They're going to get farther away and attract the positive charges. It polarizes the wood and thus attracts. That's why it sticks there. Yeah.
So in one sentence, induction is?
Charging something through indirect contact. Yeah, conduction is directly and induction is not.
So when you negatively charge something, it repels the electrons and attracts.
Yes, yeah. The balloon is negative. So the individual atoms, the electrons and protons in the wood, you picture them in their atoms, they kind of shift, and all the negatives kind of point that way, shift that way, because they're repelled by the negative balloon, leaving more positives pointing towards it. And let's go back to Coulomb's law. Here's the balloon. So the balloon still has positive charges in it. It just has more negatives than positives. So it's negative. And the individual atoms in the wood kind of rotate like that. They become polarized. And you see that the positive sides are closer than the negatives. So the force is stronger for attraction than it is repulsion. Both forces are there. It's attracting the positives, repelling the negatives, but the positives are now closer. And so it can stick to the wall and attract. Yeah?
So if you got another balloon and did it with that silk thing on the other side of the door, would that stick?
I'm glad you asked. If you were to charge the balloon positive, which I don't know how to do, but if you were, would it still stick to the wall? If this was positive, what would it do to the positives? Leaving the negatives closer, would it attract? It would still attract. This is still polarized, this is still polarized, but they're polarized oppositely. Different materials. Remember that one likes to grab electrons more than the other? And rubber really likes the electrons. It likes electrons more than hair and silk. If I could find a material that likes electrons more than rubber and rubbed it with that, then it would take them, leaving it positive. I'll look and see, but yeah, between these two, this likes electrons more than this. Glass. Yeah, this likes electrons more than this. But that likes electrons more than this. And this. This one. It's fast, don't worry. Okay, do you think the 2x4 is charged? Good, it's not, it's neutral, they're balanced. So I'm going to bring the negative rod near it, and it does what to the 2x4? It polarizes it. And it's attracting. I can rotate this whole piece of wood with this electrostatic force. Coulomb's law at work. Just with some charges. I know you guys don't have rabbit fur and rubber at home, but maybe you have an oven bag and a pink flamingo. Still works. It's going to fall off, isn't it? All right, if you weren't here, come get your test, and I'll work on those, and have a great weekend.